Hello everyone, so let's now do the analysis of the Build-heap runtime algorithm. So in last segment we discussed that seems like the algorithm should work in n log n, okay, but here interestingly the runtime is actually order of n. So it seems like a magic, but the idea is actually kind of we can prove that using calculus, but before going to too much mathematical proof, we are going to give you the idea why the runtime is order of n. Okay, so our tree actually a complete binary tree. It looks like this. Okay, so in the reverse level order we are going to do the heapify for each of the node. Now in the last level, as every node is already a heap, we are not going to consider them. Okay, all right. So now the heapify algorithm or parallocate down algorithm actually depends on the height of the node. So for example, for this node has height 1. Okay, so this node has height 1. So for when we are going to do the heapify for this node, the runtime will be order of 1. Now any node in this level, okay, any node in this level, all node in this level, they have height 2. Okay, so for any node in this level, the heapify algorithm or the parallocate down algorithm is going to be order of 2, and for the root node the algorithm will be order of 3, because the root node has here height of 3. So now let's just see that what is going to be the maximum number of operation we are going to do. Okay, all right. Okay, now we are going to consider the worst case runtime. Let's see how that is going to look like. So in this level we have 8 node. So for this particular tree we have 8 node with height 0. Okay, in this level we have 4 node with height 1. So in this level we have 2 node with height 2. Okay, and in this level we have 1 node with height 3. Okay, so for this particular complete binary tree, let's see in worst case we are going to do the parallocate down algorithm. We are going to implement the parallocate down algorithm for each of the node. Okay, each of the node from height 1 to height 3. Okay, so for each node here, okay, we have total 4 node, and the operation is going to take order of 1. Okay, so the runtime will be here. For this level we have 4 node and the runtime is order of 1. So here we have 2 node. All right, 2 node, and if for each of the node the runtime operation is at best order of 2. Okay, so 2 node and order of 2. So and in this level we have order of 1 node and the runtime is going to be order of 3. Okay, so 1 node times 3. So how many operation I am going to need? Okay, so how many operation I am going to need? This is going to be 4 plus 4 plus 3. Okay, and this is 11. All right, so we can actually generalize this approach like that. So if we have total n nodes in a complete binary tree, okay, the number of operation, or in worst case the number of operation is going to be always less than n. All right, so here we need the 11 operations. So and with n nodes, the number of operation we are going to need, we can actually generalize by as a n minus h minus 1. Okay, so as a n minus h minus 1, and you can have a proof here from like that. say here the n equals to 15 and height equals to 3. Okay, so for this tree we have n equals to 15. N means the total number of node in this tree. Okay, n equals to 15, height equals to 3, and the total operation we are going to need 15 minus 3 minus 1 equals to 12 minus 1 equals to 11. Okay, so we can generalize this approach. You can generalize the number of operation based on the number of total nodes and the height of a tree. Okay, and this will be always n minus h minus 1. Okay, so if this is n minus h minus 1, means in worst case our runtime is order of n minus h minus 1, means order of n. Alright. Okay, so this is just a general view, general idea, very simple idea how we can visualize what is going to be the runtime of a build-heap algorithm for a binary tree, binary heap. Okay, so now we can actually prove the idea that the runtime will be always order of n. Okay, so we are not going to go too much detail into the proof, but we are going to give you the idea. We are going to give you the idea how the mathematical proof is going to look like. Okay, all right, so let's say our tree looks like that. Say a complete binary tree looks like this. Okay, so first of all we have to know few of the properties of a complete binary tree. Okay, so in the last level, I mean in the leaf level, every node has a height 0. Okay, so for a complete binary tree, here for this tree we have 8 node with height 0, and here in this level we have 4 nodes and each of the node has height 1. So in this level we have total 2 nodes and each of the node has height 2. So in this level we have in the root level we have 1 node and it has height 3. So if we know the total number of nodes, say n is the total number of total nodes in a complete binary tree. Okay, and if we know the height, okay, so in a given height, okay, in a given height h, what is the maximum possible number of nodes in the tree? So n is the total number of nodes in a complete binary tree. Okay, it is given, and in a given height h, so what could be the total what could be the maximum possible number in a given height h? Okay, so this equation is actually n divided by 2 to the power h plus 1, and we are going to take the upper bound. So in a given height h, this is the maximum possible number of nodes in a complete binary tree. Okay, so for example with height h, with height 0, in 0 height how many nodes we can have? So in height 0 we are going to have n. So in this example we have total 15 nodes, so n equals to 15. So in height 0 we can have how many nodes? 15 divided by 2 to the power 0 plus 1, and if we take the upper bound, the number is going to be 15 by 2 is 8 nodes. Okay, so with height 0 we can have at best 8 nodes. So with height 1 we can have at best 15 divided by 2 to the power 1 plus 1, 15 divided by 2 to the power 2 means 4 and 4 nodes. Okay, so we are taking the upper bound means ceiling function. So with height 1 we can have at best 4 nodes. So same as like with height 2, we can have 15 divided by 2 to the power 2 plus 1 means 2 to the power 3. So 15 by 8 equals to 2 nodes. And with height 3 we can have 15 divided by 2 to the power 4 means 16, so which is 1. Okay, at best we can have 1 node. All right. Okay, so how we can prove that? So in each of these height level we can have this many, at best we can have this many number of nodes. Okay, and for each node at a height level, the operation takes the heapify operation is actually proportional to the height of the node. Okay, the heapify operation is proportional to the height of the node. So for example, this node has the operation is proportional to the height of this node, which is order of 1. So worst case runtime for heapify algorithm for this node is order of 1 because height is 1. So for each node, the heapify algorithm has the runtime which is order of h or order of log n. So let's just consider order of h. Okay, order of height. So in each level we have n divided by 2 to the power h plus 1 node, number of node, and for each node the runtime is order of h. Okay, so the h is the height of this particular node. All right, so this is the runtime of node at each different level. Okay, it in each different height. Okay, so for example, in this height we are going to have total 4 node, and for each node we are going to have the runtime will be order of 1. So this node, this level, and this level, the total number of node is this one, n divided by 2 to the power h plus 1, and for each of the node the runtime is order of h. Okay, so here the runtime will be order of 2. Here height is 2, so order of 2. But here what we are saying, this is the total number of node at each height level, and this is for each of the node. For each of the node, they are going to have the runtime will be order of h for each of the node. Okay, all right. Now how many levels we can have? So this is the runtime for each height level. Okay, so this is the runtime for each height level. So this is for each height level, this is the total number of nodes, and this is the runtime. Okay, now how many height level we can have maximum? So if n is the total number of nodes in a tree, how many levels I can have? Okay, so this could be log of n. So how many height levels, how many levels we can have? This is going to be log of n. Okay, so what we are going to do, the runtime, the worst case runtime is going to be, height will be from 0 to log of n. So here actually we are still considering each of the node at height 0. So let's not ignore anything. We are going to consider each of the node from height 0 to height log of n, and log of n is going to be the maximum height. So what we are doing, for each level we are taking the total number of nodes and their runtime. Okay, so this is actually our runtime for build-heap algorithm. Okay, so this is the runtime of our build-heap algorithm. Okay, all right. Now we are going to see how this is going to become order of n. Okay, all right. So we saw that our our runtime for build-heap algorithm looks like this. Okay, so summation of from height 0 to log of n, this is the maximum height, and n divided by 2 to the power h plus 1 upper bound and order of h. Okay, all right. So here we can write that as a log of n summation of h equals to 0 to log of n, and here we can write that n divided by 2 to the power h times 2. Okay, order of h and order of h. So this is order of h, means we can here write as a like a constant number and ch. Okay, so this is order of h, we can write as a constant number, any number c and h. Okay, all right, from here to here we can write that. All right, so what actually we can do here, we can take the cn divided by 2 out. Okay, so we are taking cn divided by 2 out, and we can write that like as a h equals to 0 to log of n, and this will be h. Okay, this is n, and this is going to look like this is going to look like 1 divided by 2 to the power h. So we're going to take 1 divided by 2 to the power h times h. Okay, all right, and this is look like cn divided by 2 h divided by 2 to the power h. Okay, so h divided by 2 to the power h. All right, now this portion of this theory is actually known as a harmonic progression. So harmonic progression. So now with the harmonic progression, like with the harmonic progression with h equals to 0 to infinity, where h divided by 2 to the power h. So the value of this harmonic progression from h from 0 to infinity, h divided by 2 to the power h, is actually the value is 2. Okay, so we are not going to prove that, but just know that this is a harmonic progression, and from h from 0 to infinity, and the value of this progression is equals to 2. Okay, now here this portion of this looks like from 0 to log n. Now log n is much smaller than infinity value. Okay, so this portion of this is going to be much smaller than this, is going to be actually a less than value of this value. Okay, which is 2. All right, so this value could be at best, this value could be 2. At best the value for this portion of this theory is could be 2. Okay, so now if the value is 2, then we can have the value here, we are going to get c of n. All right, and that's how the value of runtime is going to be, and this equation, the runtime equation, is going to simplify it to order of n. All right, so that is the idea, that first when we saw the algorithm, seems like it should be like n of log n, but like it's not, like a magic, and the order of runtime, the real runtime, is actually a linear time algorithm. It's actually a linear time algorithm, and the runtime is actually order of n. Okay, all right, so so this is the idea, and that's how actually we show you actually two way how we can prove that the runtime of build-heap algorithm is order of n. Okay, so I hope you guys actually understood how we actually got this order of n runtime solution, and I hope you guys enjoyed that. Okay, So in last class actually we already discussed about heap sort and the analysis of heap sort algorithm also, and we discussed that actually we use the uh, mean heap. Okay, we use the heap algorithm, binary heap, as a implementation of priority queue. Okay, all right. So here at the last of the few slides are actually about few of the algorithms, few of the problems where we can, few of the problems that we can solve using heap. Okay, using mean heap or max heap. Okay, so most of the problems actually have been solved using mean heap. Here this problem is using a max heap. So I'm going to actually leave all of these problems for your homework. So by homework means your self-study. Okay, so go over all of these problems and try to understand how actually we did solve all of this problem. Okay, so at the end of the semester, if we after we discussed all of the module, means all of the topics, if we have enough time, we are going to actually come back to couple of these problems and we are going to discuss about them. All right, all right. So in this topic in heap, we discussed what is a heap. We have two versions of heap, max heap and mean heap. So in the heap we have two operations, insertion and delete max or delete mean. Okay, by delete max or delete mean, so in the mean heap we are going to implement delete mean, in the max heap we are going to implement delete max. So the delete mean or delete max, they are actually equivalent to the operation of taking the taking the value with the most priority. Okay, so in the delete, in the mean heap, it seems like in the priority queue implementation, in the mean heap algorithm, the value with the minimum value is the value with the most priority. So in the max heap, it says that the idea is that the value with the maximum value, okay, in the root, it has the maximum priority. So here the delete mean or delete max is equivalent to the operation of taking the value with the maximum priority. Okay, and we saw the build heap algorithm, and the build heap algorithm has order of n runtime, and we saw how we can implement the heap sort algorithm. Okay, so that is actually for now, that is all about the topic of heap.